Hello! So, in this video I just wanted to do a quick recap of the basics, the kind of general idea with systems of linear and non-linear equations, kind of what the idea is, why we do what we do, just kind of a quick recap basically. So, we've got our system of ODEs. Now, what are these systems actually saying? Because I don't think I've really talked about that so far. This is just basically saying, if we've got a function, okay, we can have n different variables, all right? Let's just say we've just got two variables, x and y. Then basically we've got what these equations mean is how our variables change over time, how each variable changes over time. So dx changes over time, and x changes over time by dx by dt. That's how it describes that change over time, and that change is given by some function, and we're just going to call that function f of xy. All right, and that function is always of our variables, right? And then likewise for y, our variable y can change over time. We call that dy by dt, and we give that, we just denote that by a function g, again of x and y. So in other words, we've got a description of how each variable changes over time. Now note that we can have, like I say, n different variables. All right, we can have as many different variables as we need, but we just usually consider the two-dimensional case, the two-variable case. Why don't we consider the one-variable case? Well, because one variable, say like I'm going to call it dA by dt, all right, that's just an ordinary ODE. Okay, the point is with these types of systems, we're looking at how the variables relate to each other, how these kind of variables over time, how they relate to each other. That's kind of the aim. We want to try and combine these two things together and kind of find out how the variables change and interact with each other over time. So the one variable case, it just interacts with itself, if you like, so it's not really that applicable. The point is that the two-dimensional case is the most useful, simplest application or case, and then the n-dimensional case will just follow on. It's the same sort of ideas. Okay, so from this then we can have an equilibrium point. From these two equations we can have an equilibrium point. Remember, we get these from setting these two things equal to zero. It's a bit like finding the stationary point of something. It's the point where sort of we're neither increasing nor decreasing. It's a stationary point. Okay, so we set them equal to zero and we get an equilibrium point, and that equilibrium point in general will be at x, y. Okay, it's just our variables. Sometimes we note it by xe, ye, right? And for convenience, we can move our equilibrium point by scaling a whole function or transforming a whole function by x tilde. And if you remember that x tilde is equal to x minus xe, okay? Effectively, we're just moving our function equilibrium point from here to here by moving it in that direction. And that direction is xe, and we move it down as well by ye, or we can move it up or down, doesn't really matter. Okay, so that's kind of the basic ideas, and then what we want to do is try and combine these two things into one kind of equation to find out how they interact over time. Now, in general, let's just look at the non-linear case, let's look at the linear case first. Okay, so in other words, when the right-hand side of these functions, this dx by dt and this dy by dt, let's just look at the case when they're linear. So we've got dx by dt, a linear function. We've got ax plus by plus some constants on the end. And we've again got dy by dt equals cx plus dy plus another constant hanging around on the end. So that's kind of the general form of a linear system of equations. Okay, and then we can combine these kind of two things into one equation. So we've got dx, just by using matrix and vector notation. So we've got dx by dt equals ax plus k, where k is just our constants on the end. Okay, and I've shown you that this is true, right? But then basically the reason why we do this is because then we can look at this coefficient matrix, this coefficient matrix, and then from that we can pull out some eigenvalues and then eigenvalues, and then from that we can then pull out some eigenvectors. Okay, so the idea is then that we're just looking at the coefficient matrix. That coefficient matrix, if you look at these equations, those coefficient matrices, the coefficients will basically define how the linear equations kind of change. Okay, so it makes sense then that we can work out how the variables change and interact with each other over time just by looking at that coefficient matrix, because the coefficients are literally what define our variables. by the way, we kind of just disregard this k just because we can transform it to the origin, which is usually what we do. We transform our equilibrium point to the origin, and at the origin our constants are 0, because if you think about, you know, a linear equation of a straight line, so y equals mx plus c, which is literally what we've just got here, okay, literally just what we've got here. Well, our c, if you like, is our k1 or a k2, yeah, it's just our intercept. And so, you know, if we're at the origin, our intercept is clearly 0, so therefore our k's just disappear. Okay, so that's just basically the idea. So the important thing is then we can look at the eigenvalues and the eigenvectors and look at how the equation changed over time. And then from that we can pull out a general solution of how these two systems of linear equations, so we're now combining the two things, working out how they interact with each other. Okay, when the combined system, we can work out how they interact over time. We're looking for a solution, general solution that looks something like this. So C1 e to the lambda 1 times t times by our eigenvector u1, and then we consider the second eigenvalue and eigenvector, so c2 e to the lambda 2 t u2. Okay, and then from this we can look at kind of the different cases for the eigenvalues, right? And then from those eigenvalues we can see which one is going to play the dominant term. Okay, so which one's going to dominate as t gets bigger and bigger and bigger. Yeah. So say, for example, let's consider the case when lambda 1 is bigger than lambda 2, right? So the case when lambda 1 is bigger than lambda 2, it means that basically this term is going to become the dominant one. You can work that out by putting in values, okay? You can clearly see that as we put in bigger and bigger values for t, this one's going to dominate. This lambda 1's going to make this one dominate, force this one to dominate, and this one's just going to basically, you know, become irrelevant, basically. So what we're trying to sort of basically saying is that our solutions are going to tend to this eigenvector. Now, I should really talk about the solutions, I suppose. The idea is that if we have, you know, n different variables and an equation for each one telling us how each variable changes over time, that can be really difficult to solve analytically, kind of using algebra. So the way that we do it is just literally to look at what's happening geometrically of each solution. And how each solution changes over time by drawing kind of the path of each solution. And we call those paths trajectories. Okay, and then basically we end up with a sketch, effectively, of how each variable changes over time. Okay, by looking at all the different paths that our variables can take. These two variables interacting with each other form a trajectory, and what each trajectory is doing over time. And then that will give us the... that will give us literally what we want. That will just tell us how each variable interacts over time. So let's consider the example where lambda 1 is bigger than lambda 2. This term will dominate. Okay, so in other words, we're wanting to become, if we draw the two eigenvectors on, so we got, let me draw it around the other way. There we go. There we go. So this now is u1, and this now is u2. So these are the eigenvectors which we drew on. Remember the nature of eigenvectors. Eigenvectors, if you like, are stripped down versions of vectors. Right, because we're not interested in direction anymore. They can go either that way or that way, so forwards or backwards. Not bothered about direction. We're also not bothered actually where they lie on the plane, so we can actually consider any parallel vector to this eigenvector. All we're interested in is literally how these two eigenvectors interact with each other, so the angle which each eigenvector forms with each other. That's all we're interested in with eigenvectors. All right, and so yeah, if over time lambda 1 is approaching lambda 2. If over time u1 becomes a dominant eigenvector, it basically means that all solutions are going to be looking like this. They're going to want to become this eigenvector. So basically we're looking something like this, right? So you're coming like this, coming like this, coming like this, okay? And then if we go back in time, then it makes sense that if we go back in time, our trajectories, so I'll just put these arrows on because we're wanting to look more like this eigenvector. You can hopefully see that this looks a bit more parallel to this u1. They're literally going to become like u1 as we go forwards in time. But then the opposite, if we go forwards in time, this one's a dominant term, so u1, although trajectories are going to tend towards u1, okay, our first eigenvector. But then the kind of makes sense that if we go back in time, then this term will become the dominant one. Okay, so in other words, as we go back in time, we would expect our trajectories to look a bit more like the second eigenvector. And if you look at this case here, that you know, we've got that happening because we've got as we go backwards in time, so we're sort of over here, okay, we've got eigenvectors which look like this u2. It's parallel to this u2. Yeah, hopefully that makes a bit of sense to you. And notice as well, there we go, it's a little bit better. Notice as well, the only place, I should have said this earlier, the only place where solutions can intersect is at the equilibrium point. So at that point there. If they intersect anywhere else, then they're not, then it's not strictly speaking a true. It can't happen, basically. I'm not going to try and justify it. It just can't happen. Basically, the only place where solutions can intersect is at an equilibrium point. Okay, and so this is my equilibrium point here. Okay, which is kind of why we get this drawing here. And yes, the only place where solutions can intersect is at this equilibrium point. All right. And so this is what we call actually when this is the case. So they're both positive or both negative, both the same sign. And if one is bigger than the other, then we call this case a proper node. There are other cases. Go back to my videos and sort of looking at all the different, I think there's 6 cases in total of all this different thing. The last thing I just want to mention is this is the linear case. Okay, now this right-hand side, this is a linear case. This right-hand side, I've said, doesn't have to be linear. So in other words, it can be non-linear as well. But we can use, I think it's called the Hartman-Grobman theorem too, off the top of my head. We can use that theorem that basically says that providing we can treat a non-linear case as the linear case. So in other words, we can do this kind of analysis by forming a coefficient matrix and finding out the eigenvalues. We can use that kind of process, the same process that we use for the linear case, for the non-linear case, providing we're close to the equilibrium point. If it's away from the equilibrium point, we have to use slightly different techniques. It doesn't work. But if we're close to the equilibrium point, then we can use this. We can use this this kind of process, find the eigenvalues, work out which term is going to dominate, so which eigenvector is going to dominate, to work out exactly what's going on. And that's only true if the eigenvalues are not equal to 0. If they're equal to 0, that's a very specific case. We have to use a slightly different technique. But if they're equal to 0, if they're not equal to 0, let me say this again. Providing that we're close to the equilibrium point, we can treat the non-linear case as the linear case, providing the eigenvalues are not equal to 0. Because that's something special. We call that basically a hyperbolic solution. So the conditions of we can treat non-linear as linear if we're close to equilibrium. If we're close to equilibrium and the eigenvalues lambda 1 and lambda 2 are not equal to 0. Okay, if those conditions are satisfied, then we can treat the non-linear case as the linear case. If we want to consider places away from the equilibrium point, then again we have to use slightly different techniques, I say. But hopefully that makes a little bit of sense. So what have we got here? What does this? I suppose the biggest point that I wanted to make is what is the point of this sketch? Well, it shows how the two variables, or how many variables we have, how variables interact with each other over time. Okay, well that's effectively what we're doing there. We're solving this equation. When we solve equations, we're showing how variables interact with each other. All right? So it's a system. We're showing how the variables interact with each other. So we're getting a sort of explicit solution. So in other words, we're finding dy by dx. Sorry, dy by dx. That's what we're finding with this trajectory graph. Okay, we're finding how. We've got how the variables change over time. So we're just now finding how the variables interact with each other. If you like, these are two separate cases. We've got this variable interacting over time is giving us this variable interacting over time is giving us this. What we want to do is combine the two things together and find out how they interact together. All right, so that's effectively what we're doing with the trajectory graph. Okay, and that will give us basically our solution. This will give us a solution for the linear case. We can also give a solution for the non-linear case, providing we're close to the equilibrium point and those eigenvalues are not equal to 0.